let's talk about rational functions. A rational function is a function that is rational. It's a ratio. Here's your key word right here, ratio. It's basically going to be something divided by something else. Now, you'll notice that when you get to number 2 and number 3. It's not that way on number 1. Up at the top of your notes on the front page, I have left lots of space for us to fill in helpful hints, definitions, and things like that. So some of these are obvious and you've heard of them before. Some of them you may not have, like this notation down here is more than likely new to you. So we're going to just jump straight into it, and we're going to revisit the first page several times and fill in some of these things. So let's just go ahead and go straight to number 1. Here we go. For each of these, do all that stuff. Let's just go ahead and graph it. You got this. X plus 2, we go up to 2. The slope is 1, so rise 1, run 1, and we're going to draw a line. There it is right there. Okay. Nothing too special, nothing really scary about that. Now let's read the directions. Sketch the graph. Done. State the x and the y intercepts. So let's do that. The x-intercept is at a certain location, and it is a coordinate, so we will write it like a coordinate. And the y-intercept. So let's just go ahead and hit that. The x-intercept is right here. It's at that coordinate. Now, if I was to ask you where is the x-intercept, you might say -2, and you would be correct, but technically it's at -2, 0. And I want to point out something really important here. The y-coordinate of your x-intercept is always 0, because if you're going to cross the y-axis, you've not moved up or down at all. So if I had an x-intercept right here, it would be at 3, 0, or 4, 0. So the y-coordinate of the x-intercept is always 0. You know where I'm going next, right? Boom. That's at 0, too. And the same thing I just said about x applies to y. The x-coordinate of the y-intercept is always 0. So let's take what we've just learned and let's move up here and let's start filling in some stuff. You know what an x-intercept is, but just in case you didn't know, here's how you find it. Plug in 0 for y and solve for x. If I want to know where the x-intercept is, then y is equal to 0. Same thing with y, only slightly backwards. Plug in 0 for x, and I'm going to say simplify in this case, because most of the time you won't have to solve, because you'll have y on one side already by itself. So in a situation like this, and you don't have to write this down, but just really briefly, in a situation like this, if I wanted to know the x-intercept, then I would say, well, then y is 0. This is y, so 0 equals x plus 2, and I would subtract 2, and so that's where that -2 came from. Okay? All right, let's move on. Holes in the graph. Nope, hadn't happened yet. Vertical, horizontal, and slant asymptotes. Don't worry, that's not on this one. Let me address this real quick. Real quick, though, let me also write one more thing. No holes or asymptotes. You'll see what that is. You'll know it when you see it. If you've never seen one before, and you have, actually. No holes or asymptotes. But we will deal with this. Let me show you what this notation means. Let me go ahead and start by kind of answering it. As I get bigger and bigger x values, what happens to y? Does it increase or decrease? Or what does it really approach? So when I'm getting bigger x values, if this graph went on forever, then my line would go up here, and it would just keep on going. It's the bigger the x gets, the bigger the y gets. And it tends to go to infinity. So this statement right here means the limit as x approaches infinity. Limit meaning I'm approaching something. I am approaching infinity. Not that I could ever get there, but as I approach infinity, what happens to the y value? Well, as x gets bigger and bigger and bigger and bigger and bigger, then the y value approaches infinity. So the limit as x approaches infinity of f of x equals infinity. Let me restate that one more time. When my x gets big, whoop, my y gets big too. It runs off the graph. And as x approaches infinity, y approaches infinity. We've answered this one. We didn't answer the first one, actually, so let's do that one. As x approaches negative infinity, so as I go this way, what happens to the y values? Well, they're going down. So the graph is going down, and as this graph goes down, the y values are getting lower and lower and lower, and therefore the limit as x approaches negative infinity of f of x, of my function, it is equal to negative infinity. Okay, I'm going to really briefly try to define some stuff up in these bubbles right here. The limit as x approaches negative infinity, that's the way it reads. So the real question is, as you move left, on the graph, what value does f of x, or y, approach? That's the question that goes with that one. And we're going to write something very, very similar here, and I'll just write it all down. If you want to put some ditto marks and change a few words, that's okay. The limit as x approaches positive infinity, that's the way it reads. And same kind of question, as you move right. By the way, some teachers call this end behavior. It's how my graph behaves at the ends. The end behavior in this case is negative, positive. It's kind of a similar idea with that. As you move right on the graph, what value does f of x approach? All right, let's move on to the second one. All right, second one. We're going to find the x-intercept, and we're going to find the y-intercept. Let's start with the x-intercept. Now, what does this graph look like? You'll see in a second. Actually, yeah, let's not. I'm trying to decide how I'm going to start this thing. Let's start by factoring. Should have started there. So if you've already written that, that's cool. But you're going to see where we're going with this in a second. Let's factor the numerator. So we have x plus 1 and x plus 2. You've done that. That's why we did the other worksheet. And here you have x plus 1. Now, you see something, don't you? You see it, don't you? All right, I see it too. We're going to mark those out. Okay. So when we mark those out, we can draw the line x plus 2. So I'm going to go one more step, and I'm going to say this is equal to x plus 2. But I have to put a little caveat in there. I love that word. I have to throw in another little caveat saying what x can't be. I can't divide by 0. I've tried, it doesn't work. Cannot divide by 0. And if I had an x value of negative 1, I would be dividing by 0. And real quickly, let me show you what happened. If x plus 1, that's my denominator, if it equaled 0, then x would equal negative 1. Okay? I cannot divide by negative 1. So even though I've marked it out, the original function had that denominator, so I can't do that. So it's x plus 2, where x is not equal to negative 1. I'm going to graph this entire thing, but I better not graph at negative 1, where x is negative 1. So we're going to draw this. Be careful when you draw this. Same graph we did a minute ago, But be real careful, because when we get to where x equals -1, I'm going to skip it. There we go. There's my graph. Now, if I was to ask you what the domain of that is, which we're not going to do right here, but if I was going to ask you what the domain is, you would say it's -∞ to -1 with a parenthesis, the little the U symbol, and then -1 to infinity. Okay, x-intercept, same as what we had. We can do this without really thinking about it too hard. X-intercept is at -2, 0. The y-intercept is at 0, 2. And now we get to some of the other questions. And I have a separate piece of paper here, and you're going to have to flip yours over. I apologize. But the directions said, find holes in the graph. Well, there's a hole in your graph. You see it, don't you? You see that hole. And that hole happened when you marked this out and you said, you know what, I can graph this line, but the original function did not exist at -1. So there is a hole at, and I'm going to give the entire coordinate. That coordinate is at -1, +1. This is going to come in handy when you get to calculus, by the way. The hole is at -1, +1. Okay? There are no asymptotes. You'll know them when you see them. So if you are unfamiliar with it, don't panic about that yet. And the limit as x approaches infinity of my function is something, and the limit as x approaches -infinity of my function is something else. So the limit as I approach infinity, as x gets bigger, what happens to the y value? It's going up. So if I kept drawing this forever, it would go up. So same graph we had, only with a hole in it on number 1. So as I approach -infinity, it goes down. There we go. There's number 2. Let's do number 3. We're going to have to factor and we're going to have to reduce. So let's keep going. Numerator factors into x plus 6 and x minus 4. Denominator factors into 2. There's a GCF. And x minus 4. You see what I see? That reminds me of a Christmas song. Let's mark them out. There we go. So it's really this you know what I'm about to write? X is not equal to what? What could x not have been in this original function? What x value would have made this denominator 0? And if you can't answer that off the top of your head, that's okay, because you can come over here on the side and say, well, you know what? If this denominator equaled 0, then I'd add 8, make an equation, solve it, and x would be 4. And it's fairly obvious from here if you just change that sign. So x cannot equal 4. It can't. So it's really this, and we're going to graph that. Before we get too crazy with it, I'm going to rewrite this one more time. Make that a 1. And we're going to divide everything by 2. See, 1x over 2, well, 1 over 2 is a half. 6 over 2 is 3. So we're really going to graph this, okay? So if this was making you angry and you're like, I don't know how to graph that, it's the same as this. And you've graphed this before. Let's do it. Now, when you get to 4, you better stop. And you better put a hole in that graph. So we're going to go up to 3. And we rise 1 and run 2. If you wanted to, you could rise 1 and run 2 more. Oh my goodness, see that open circle? You know why? I just said it. It's because of that. So here's your line. There it is right there. All right, let's start finding some things that we need to know. We need to know what the x-intercept is. If you drew this correctly, it's sort of staring you in the face. It's at -6, 0. If you didn't draw it correctly, then what you could do is plug in a 0 for y and solve this for x, which would get a little complicated in the process. But long story short, I'm going to use this one instead. I'm going to say that this is my function. And I'm going to say that if I didn't know this was -6 and I was really sloppy when I drew my graph, then I could go 0 equals 1/2 x plus 3. I'm just following these directions right here. That's all in the world I'm doing. We're going to subtract 3, and we get that. We'll multiply by 2. Gives me -6. So my x-intercept is at -6, 0. My y-intercept is 3. It's clearly 3. So it's 0, 3. All right. There is a hole in my graph. It is at a certain coordinate. It is at 4, 5. There are no asymptotes. You'll know them when you see them. Trust me. And the limit as x approaches infinity of my function is, okay, as this thing gets bigger, what's happening to x? What's happening to y? As my x values increase, what's the y value doing? It's also increasing, so it's approaching infinity. Now, I want to go ahead and say this as another caveat. Just because it's increasing doesn't mean it's approaching infinity, but for our purposes right now, that is true. So as I approach negative infinity, as my x values get smaller, what's happening to the y value? It's going down, which in our case means it's going towards negative infinity. Okay, I am not going to finish 4. I'm going to start it. This one's going to be a little interesting, but I'm going to let y'all finish this one on your own. First of all, what can x not be? It can't be 5. Yeah, it can't be 5. So x and then x minus 5. GCF on the top, by the way. That's why I did this one, because it's slightly different. So we'll do that. And we'll say that this really is the line x, where x cannot equal whatever would make my denominator 0, which would be a positive 5. Okay? I'm going to leave the rest of that one up to you. There are no asymptotes on it. There is a hole. Let's see. These are going to be pretty straightforward for number 4. So if you want to pause the video right now, you can. And yeah, you can do that and do number 4. I'm going to move on to number 5, however. So start the video back whenever you're ready. All right, number 5. Number 5. Let's factor. Numerator breaks up into x minus 3 and x minus 5. Does anything cross out? No, it does not. It absolutely does not. This one is going to get a little bit crazy. And that is okay. That is perfectly okay. So, here goes. Let's draw the graph. This one will require a graphing calculator or Desmos. I recommend both. I recommend Desmos for the clarity of the picture. I recommend the graphing calculator so you'll really be used to it when the time comes and you can't use Desmos. I wish you could carry Desmos with you the rest of your life. But as of now, you can't. So I'm going to use a graphing calculator. X squared minus 8x plus 15 divided by, make sure you put it in parentheses if you're using your calculator. Please put that numerator in parentheses. Put the entire denominator in parentheses as well. And we're going to press graph. Wow. That one's crazy, isn't it? That one is quite crazy. This one has 2 asymptotes. One of them is a vertical asymptote, and I told you, you know it when you see it. Clearly this is not a line. And an asymptote does this, just like that right there. It approaches a value and gets really close to it, but never necessarily crosses it. There are some random ones that do, but we won't go there quite yet. And it has what's called a slant asymptote, because it's sideways like that. All right. Let's go ahead and just start with the x-intercepts. And once I have a little more information here, then I'll start filling in the graph a little more accurately. So the x-intercept is everywhere. The x-intercept is everywhere that y is equal to 0. So we're going to go 0 equals x squared minus 8x plus 15 over x minus 4. Okay? And we have to solve that. Don't panic. It's not nearly as hard as you think. Trust me. We're going to solve this and find out what our x-intercepts are. Now, you can look at your graph and tell where they are. I'm going to go ahead and tell you. They're at 3, 0, and 5, 0. But if it's not obvious, here's how you'll find it. Put that over 1 and cross multiply. 0 times that gives you 0. 0 times x minus 4 gives you 0. 1 times all this mess gives you, well, all this mess. You can use the quadratic formula on that, but why waste your time when you've already factored it? You know what it is. It's x minus 3, x minus 5. And we will solve each piece. We're going to set each piece, each factor, equal to 0 and solve it. So x is equal to 3 and x is equal to 5. Therefore, we have two x-intercepts. One of them is at 3, 0. The other one is at 5, 0. I'm going to go ahead and start making my graph. There's one of them. There's the other. Okay? We know that so far. Let's find the y-intercept. The y-intercept is easier. It is where x is 0. So we're going to take this same equation and we're going to go y equals 0 squared minus 8 times 0 plus 15 all divided by 0 minus 4. This actually ends up being really neat and nice. 15 over negative 4. That is a little below 3. So this is equal to negative 3 and 3/4. There we go. Yeah. So this doesn't have to be perfect, but just as close as you can get it. Negative 3 and 3/4. There it is. Okay. So far, we have not sketched the graph, stated the x and y intercepts. Are there any holes in the graph? No, and here's why not. There was a hole in the graph where this occurred. I'm looking at number 3. There was a hole in the graph where this got marked out. I'm looking at number 2. There's going to be a hole in the graph here on number 4 at 5 comma something. Nothing here canceled. There are no holes in the graph. But there are asymptotes. An asymptote, here's the rough definition. An asymptote is where it approaches something. I said this a minute ago, but it's where it approaches something but doesn't actually touch it. So, first thing, a vertical asymptote, they occur where the denominator equals 0. So, on this one, what would make your denominator 0? 4. 4. So there's going to be a vertical asymptote at 4. So if I wanted to draw my graph at this point, I could. I choose not to yet, but I'm going to go ahead and write that down. I'm going to call it VA for vertical asymptote. My vertical asymptote is this dotted green line right here, and it's x equals 4. You know what I just realized? On my y-intercept, I didn't write it like a coordinate. I failed. There we go. We found x-intercepts, we found y-intercepts, we have no holes. There's a vertical asymptote. There is no horizontal asymptote. It looks like it's not funny because it's like no ha. Let me show you the graph one more time. This thing does not level off horizontally. I can't lay my ruler down and be like, see where it levels off? You can't do that. I can do that vertically. I can do that with a slant asymptote, which we'll discuss in a second, but I can't do that horizontally. That's why it has no horizontal asymptote. Okay, slant asymptote, here's the crazy one. I need to know exactly how this thing is leveling off, and here's how I'm going to find it. Watch closely. You've got this. Look at where I'm pointing and look at what I'm writing. 4. 1, -8, 15. Look familiar? I tell you, there's a lot of stuff embedded in these problems. We're going to bring down that 1. Multiply. Put it there. Add. Multiply. Put it there. Add. This is your remainder. Okay? Why did I do that? Before I answer that question, let me tell you what I did. I used synthetic division on the original problem. I changed the sign of the denominator. There it is. It's staring you in the face. It's already on your vertical asymptote. It's just the opposite of that. And then you listed your coefficients. 1, -8, 15. Bring it down. Multiply, put it there, add. Multiply, put it there, add. Here's your answer. My slant asymptote is at y equals, check this out, 1x minus 4. What about the remainder? Don't worry about the remainder. In this case, you do not worry about the remainder. So I'm going to draw this thing just as beautifully as I can. Here goes. I'm telling you, this stuff is crazy. I'm going to draw this one with a green line. Down to 4, slope of 1. And here's my vertical asymptote. I'll make it solid green just because I feel like it. So here's the graph. Here's a really good, accurate graph. It's never going to cross that green line here. It never crosses that green line either. And then it comes up from here. It does that. There we go. Number 6 is very similar to number 5. I'm going to skip it, and I'm going to go down to number 7. That'll be the last one on this video. Okay, number 7. Let's start by looking at it and seeing if anything marks out. Nope, it doesn't. Now, if you're tempted to mark out these X's, then bless your heart. Just don't. Just don't. So, let's start with the x-intercept. The x-intercept is what you get when you plug in 0 for y. So 0 equals x minus 2 over x plus 2. And you will cross multiply. 1 times that is, well, that. 1 times that numerator. And then 0 times that denominator is 0. So x equals 2. Therefore, my x-intercept is at 2, 0. Is at that coordinate right there. The y-intercept is where the original function has zeros in for x. So it's 0 minus 2 and 0 plus 2. And I have negative 2 over 2, and that gives me negative 1. Therefore, the y-intercept is at 0, negative 1. There are no holes. No holes because I never marked any factors out. Never marked out any common factors. There are asymptotes. we could look at the graph, but before I even do that, I know this much right here. My vertical asymptote is going to occur where the denominator equals 0. After this problem, we'll finish filling all this in. My denominator is this. It occurs where that denominator equals 0. So this is the equation of my vertical asymptote. If you wanted to, you can go ahead and draw it. There it is. I will never cross that green line. I'll jump over it, but I'll never draw a graph across it. Let's see. Let's see what it looks like before we go any further. X minus 2 in parentheses divided by x plus 2. And we graph it. See that? Isn't that nice? Yeah, I like that. I like that. So if you wanted to, you could lay a ruler down and say, see that vertical asymptote? You can also say, hey, I have a horizontal asymptote. You see it? Do you see where it levels off? It's right at, and this is clearer on Desmos, but it's right at 1. And if you wanted to, yeah, it's working. If you wanted to, you can go to the table and scroll up and scroll down, and you'll notice that these values, the further you go, they get closer and closer and closer to 1. So as I went back pretty good ways, I got close to 1, but will never actually touch 1. As I scroll to bigger values, then I get closer and closer and closer to 1. See, look what's happening. See, these numbers are getting bigger and bigger. They're getting closer to 1. So y equals 1. Why is it y equals? Well, if I was to graph it, the horizontal asymptote would go like this, and the equation of this line is y equals something. Okay. Nowhere in this graph did I ever say, oh, see how it's approaching like a slant sort of thing? Like this one. See, it was clearly slanted. But in this case, it was horizontal or it was vertical, but it was not slanted. So there is no slant asymptote. Okay, one more thing to find. Well, two more things. And I didn't do this on number 5, and I forgot. I'm going to go back and do it. The limit as x approaches negative infinity of f of x. The limit as x approaches positive infinity of f of x. So let's finish graphing it. I don't need the graph anymore. I don't need the graphing calculator. Let's see, 2, 0, 0, negative 1, and it goes like this, levels off, approaches positive 1 here, there we go, looks like that. So, as x gets really, really, really small in a negative way, as I'm approaching this, what is happening to the graph? Now, it's kind of a trick question because it doesn't look like the others, but it's actually getting closer and closer and closer to that value. So the limit as I approach negative infinity is getting closer to 1. See, on the other ones, which I'm about to write this down, it was approaching infinity or negative infinity. Here, it's leveling off at 1. Same thing happens here. As I approach positive infinity, as I get bigger and bigger and bigger x values, this thing's going to get really close to a value of 1. Okay? I'm going to go back and finish 5 because I failed to do that. I apologize. So the limit as x approaches negative infinity of f of x, in this case, as I get smaller x values, it goes down to negative infinity. Oops. Limit as x approaches positive infinity is, well, positive infinity. Okay. Let's go back to the front page. I'm almost done. Let's fill in everything else. Holes in the graph. They occur when a factor cancels out. Horizontal asymptotes will be evident from the graph. So I don't have a really good hint on this one other than look at the graph and compare it with the table. You know, like a minute ago when we scrolled up and down in the table here when we did this? With the table. Compare it with the table. For the slant asymptote, look at the graph. Wow, I'm blending two words together. Look at the graph. And if necessary, use synthetic division and discard, for reasons that will be explained later, discard the remainder. Okay, I know this was a lengthy video and it had a ton of information in it. I realize that. This is a 3-page packet. I would like for you, based on what you've gathered from the few problems that you've seen in the video, I would like for you just to look through this packet and do the components that you know to do. For example, sketch graphs if you need to. If you really know how to find x and y intercepts, find that. If you know how to factor and find holes in the graph, find holes in the graph. I would like for you, to the best of your ability, to go through this and do as much of this as you can. And some of it is going to look like things that you've seen in the previous examples. The rest of it might be a little tricky at times, but overall, I think when you tackle it, you'll see a lot of similarities between these problems. So do as many problems or components of the problems as you can.